So here's some example. Now this is actually a monthly summary from the Atlanta Weather Bureau, and this is from 1950. It's in August, and this was actually typed up back in 1950, and this is just one example. It got these that go way, way back, and it's stored in there. Now it was on paper, but now they've got these pictures, and then they've also paid people to go back and extract the numbers so that you can actually go online and just bring down the data in a format that you can put into a computer and run. So here you have the date, 1st to the 31st of August, the maximum temperature, the minimum temperature, the amount of precipitation. So for example, on August 25th, they had a high temperature of 87, low temperature of 66. They had 1.87 inches of rain. They didn't have any snow in August, which is not surprising. And then you have days with rain. So they summed, and these are all summed up down here. Here's the mean temperature, the max, the min, the mean, the total precipitation for the month, all those things that are carried there. So when you listen to TV Weather Guy at night and he tells you that you know, this is the coldest October 26th since 1924, it's because of these data that are all kept there. So that's how they did it the old-fashioned way. Now here's a more modern one. This is just a day's worth of data, and this is from September 30th this year. So this is just a few weeks ago, and this is all done electronically. So we can go back in there, and these are the local standard times. That's 8 minutes before 1 in the morning. And it tells the sky condition, the visibility in statute miles, the weather type, that would be rain or fog or snow or smoke or anything like that. There wasn't any. Here's the dry bulb temperature. Now it's in Fahrenheit and Celsius, the wet bulb, the dew point, and the relative humidity, so that's all calculated. The wind speed, miles per hour, the direction, gusts, the pressure from the barometer. Here's the pressure trend, whether it was going up or down, those are codes. The net 3-hour change, up or down. Here's the pressure corrected to sea level, and then any precipitation totals. And then the last thing is just altimeter setting. That's just another barometer, but it's one that the pilots use to tell how high they're flying. So that's a more modern, these aren't typed up by hand, the computer all does it for you. And then here's some other kinds of climatological data. This is also from September 2008. Here's a monthly summary. So you can see the weather, rain, drizzle, smoke, what days. So this is all done by computer now, which does it much faster and more accurately. Then there's another new way that we get data, and that's from remote sensing. And radar I have not included because radar data doesn't really lend itself much to climatological study, but two things do. One is satellite information, and we have two kinds of satellites, polar orbiting satellites and geostationary satellites. Now the nice thing about geostationary satellites is we put them in orbit over the equator, and they are at just the right altitude, so they orbit every 24 hours. So it appears that they're always over the same place on Earth. So we can get pictures from these every half hour, actually more often if we want to. We usually get them every half hour. And then the polar orbiting satellites orbit over the poles, and typically they stay in the same plane, but the Earth rotates underneath it. So they'll pass over each point twice a day. Once going up and once going down. Now, the limitation of geostationary satellites, since they're so far away, the resolution of their images is not as good. Just like, can you read that chart over there? Not very well, but if you went right up to it, especially your age, guys like me, I have to put my reading glasses on, but people your age, you can read it pretty good if you're close. Back here it's hard. Well, same thing here. Our pictures are a little fuzzier because it's so far away, but you get them a lot. And then with the polar orbiters, they're at much lower orbits, so you get much, much sharper images. And there's a trade-off there. Well, then we have another thing, these unmanned aerial vehicles. And we can send them up for a period, and you can get very high resolution images. And they can stay, they can stay orbiting over one point for an extended period of time. So, what can we do with these? We can do all sorts of things. We can measure temperatures, not like you would with the thermometer, but by measuring the intensity and the wavelengths of the radiation. So here's a plot of humidity, and this was made from geostationary satellites over the equator. And you can see these are colored, coordinated here to give us humidity pictures. And this was taken, again, on Friday. That's when I put all this stuff together. So you can see, here we were with a lot of clouds and a lot of humidity, and then we saw these areas back here that are very, very dry. And then we can store these data numerically. Here's another thing from remote sensing. What this does is it gets satellite-derived wind fields and temperature distributions. And this tells us temperatures of the cloud tops or the surface in Celsius. So out here we're seeing clouds. You can tell what temperature the cloud tops are. Here's another thing where we've measured atmospheric instability. In other words, instability is a measure of how easy it is to make a thunderstorm. So by using satellite imagery, instead of sending up balloon soundings twice a day, we can get updated measurements of stability by measuring the temperatures at the bottom and the top of the atmosphere. Here's another picture showing cloud amounts, and so you see effective cloud amounts, and so you can see the areas. You can see the areas that are cloud-free and those that have high cloud amount. Now that has a lot of implications on climate, in that temperatures underneath clouds are going to be cooler than areas that are getting a lot of sunlight. And as a matter of fact, one of the main things that goes into climate is the amount of sunlight that's reflected back into space. We've got a fancy term for that, albedo, but the more cloud, the more solar energy goes back into space, and the cooler the planet's going to be. Another thing that we can do with satellites is we can measure biomass burning. So you can actually see fires with the satellites. So here we see, now this was back about 11 years ago, but here we are in the Amazon rainforest, and we can keep track with satellites with how much biomass burning is going on. Biomass burning does two things. It makes carbon dioxide. The trees and plants are the primary method of removing carbon dioxide from the atmosphere. Plants take carbon dioxide and water and turn it into organic material. Okay? So, for example, if you plant a tomato plant, that tomato plant takes water, carbon dioxide, and makes tomatoes. Then we eat tomatoes, and we convert it back into carbon dioxide and water. Okay, so that's the way that cycle works. Well, when you burn the trees, not only do you turn the trees into carbon dioxide, but you reduce the capacity of the forest to remove carbon dioxide from the air. Plus you change the albedo, the reflection. So many things that biomass burning does that are going to affect temperature.